Okay, so we're talking about mean curvature. And mean curvature is a very useful concept. I mean, Gauss curvature is intrinsic curvature. So just to summarize where we are, we have, K, which we call Gauss curvature. And examples of Gauss curvature: a sphere of radius r has K equal to 1 over r squared. A plane has K equal to 0. And then to get negative curvature would be like a saddle. Maybe what I'll do, I'll draw a donut, because we know the integral of the Gauss curvature is 0 on a donut. And so what I can do is I can say right here we have sort of on the inside part of it here, right? Let's say here and here, right? We have K less than 0 on the inside part. And the reason is that you see you have these. You can see that the K1, K2 have opposite signs. See how it's curving this way when you're going around this circle, but then it's curving this way when you're going through the vertical slice, right? So if you think about this point in here, right? Think about the unit normal coming out. And then you've got sort of this cross-sectional circle here, and then you have that cross-sectional circle there. Do you all see it? And one's curving one way, and one's curving the other way, right? And so the question is, well, which one do you want to call positive curvature? Doesn't matter. K1, K2 will have opposite signs, and so therefore their product will be negative. Fair enough? And also you can get that with a saddle. So, I mean, I just haven't practiced drawing a saddle, all right? But it's like a Pringles potato chip a bit, right? But if you have this curving down like that, and then this is curving up like that, right? You can have sort of a saddle that has negative Gauss curvature as well. But then also the thing is, you can take a 0 Gauss curvature thing and roll it up and get a cylinder. This also has 0 Gauss curvature. And so this Gauss curvature is intrinsic. In other words, this Gauss curvature, in fact, is just curvature. It is all the curvature there is in terms of intrinsic geometry. So if you're a blind ant walking on any of these surfaces, if this ant is a mathematician ant who's had Math 421, they will be able to plug into that formula with the F and G's we produced last time and compute what the Gauss curvature is at each point. And it will have a meaningful content. The content is that if you're on the flat space where K equals 0, it doesn't matter this is curved, I can still make graph paper out of it. In other words, I can draw a square, right? Let me see if I can, because there's this, right? I can draw a square like this as well, right? I can put graph paper on this, right? I can stack squares, right? You guys know what I'm talking about? Like in the same way I can stack squares over here, right? Stack squares and get graph paper, right? I can stack squares over there as well, can't I? Right? Now what is a square? A square is you start at a point, the ant starts at a point, they go 1 centimeter, they turn 90 degrees, go a centimeter, turn 90 degrees, go a centimeter, turn 90 degrees, come to a centimeter, and come back to where they started. And actually, that experiment will work on anything with K equal to 0 everywhere. So locally, assuming you don't go around some loop or something like that. Okay, so that's when K equals 0, then that you can make these perfect little squares. But if you try that same thing on a sphere, it turns out that what will happen is you'll go an inch, go an inch, go an inch, and then go an inch, and it will actually overshoot, even though these are all 90-degree angles. Okay. Here, you start at this point P here, you turn 90, turn 90, turn 90, you come back to the point where you started. You'll overshoot in the case of positive Gauss curvature, and then if you do a sufficiently tiny square, and then on negative Gauss curvature, you'll actually undershoot. Okay, and these will all be 90-degree angles, and you won't be able to close the square up. Okay, so that's one way where you can say, okay, this is like physical, right? Like an ant can do this experiment, right? This is not theoretical, right? This is something that's important to the ant's world when they're trying to do geometry, right? Another way to understand it is if you look at a triangle here. You guys know there are 180 degrees in a triangle, right? Do you remember how to prove that there are 180 degrees in a triangle? It's not a bad thing to remember how to do. It's like you draw this line through the vertex, and then use the fact that when you have a line that cuts two parallel lines, remember you have the base of the triangle. This line here is by definition parallel. Okay. Now we're using Euclidean geometry to say, look at the parallel line, right? There's no such thing as a parallel line in spherical geometry, for example. Okay. And so then the point is that if this angle here is x, y, and z, then you know, guys, opposite interior angles, right? That these angles are all the same, right? And so therefore, this angle x is the same as that angle x. This angle z is the same as that angle z. So these angles here add to 180 degrees. So x plus y plus z is 180, but x, y, and z are the angles of the triangle, right? Okay. So for k equal to 0, when you have a triangle, the sum of the angles, so I can say x plus y plus z is equal to 180 degrees, which we could, by the way, in radians is pi. Pi radians, right? And 180 degrees is a made-up number, right? People just chose it because they liked it because it's highly divisible, right? Pi is what an angle is, right? That's the distance. Radians are the distance on the unit circle corresponding to that angle, right? So it's the natural thing. What's interesting here is that if you have a triangle, you know, in a positive curvature case, it turns out that x plus y plus z is bigger than pi. And if you have a triangle on one of these hyperbolic spaces, it turns out that x plus y plus z is less than pi. So we call that an angle deficit or an angle surplus. Yes?
So how would an ant on the surface actually be able to calculate F and G?
First, they would arbitrarily choose a set of coordinates, like latitude and longitude, like we do. Our latitude and longitude are completely arbitrary. We arbitrarily define where the North and South Pole is, all this other stuff, right? There's not even actually a sphere, right? It's ellipsoid, right, approximately. And so we come with, and so we can choose any coordinates you want, doesn't matter. And then once you have that x of u v, right, compute x of u and x of v, right? These so what the ant then says is, okay, what's the length of xu? What's the length of xv, right? Which is really talking about dot products. And so actually, the ant can still take dot products of vectors. Maybe probably the easiest way to describe how an ant could do it, because I think I can get to your question, is to choose coordinates where xu and xv are perpendicular, like latitude and longitude. That way f is 0. And then e is defined to be the length of xu squared, and g is defined to be the length of xv squared. And what's xu? Well, okay, suppose I am at a point and I keep the latitude fixed, but I go at unit speed with increasing longitude. How fast are you going? And that's an ant. The ant can answer that question. How fast you're going is what the length of xu is.
Could you also do it just like entirely empirically, just by planting a flag, taking like 10 steps forward, making a right turn, 10 steps forward, right turn, 10 steps forward, or something like that, and then like seeing how far you are from your flag once you're finished, like to the.
Oh, to compute k and stuff.
Compute k and stuff.
Yeah, to compute k and stuff, yes.
Oh, okay.
You can do experiments like that as well.
Okay.
So yeah, you can compute the EF and G, you can compute the flag. Now, you have to know calculus, really. Like, if EF and G are, like, there is like a point, like, okay, I've told you how theoretically you can define EF and G for the ant.
Mm-hmm.
And so, this is asking for a lot from the ant. So if you're like, wait a second, but this ant's on a curved space, and so it's going to be confusing for the ant. Yeah, exactly. And guess who the ant is? We're the ant, right? When we're doing general relativity, we're doing what you asked. Right there, you asked, how does the ant do general relativity? Right, because their universe is curved. Right, and we're in a curved universe. So it is a bit of a project. But yes, but EF and G are, in theory, something that the ant can determine, given a coordinate chart. And then from that you can compute K, for example. But probably an even better way is to really think of K as this. Actually, K comes from these things here. There's actually a formula, let me just say for the record, that if you have constant K, the angle xs here, if you do x plus y plus z, minus pi. This is equal to k times the area if you had constant k. And down here, and by the way, actually the same is true everywhere. This formula is true in all three cases, okay? So then you can see why if this is for k constant. Because if k equals 0, then you see that there's no angle excess. K equals 0, sum of the angles adds up to pi. If k is positive, then whatever that small area is, that's how x plus y plus z exceeds pi by that much. And if k is negative, then you can see x plus y plus z is actually less than pi. And how much less is, in fact, the area times k, up to that sign. Okay. And by the way, this statement here follows from the Gauss-Bonnet theorem, which is sort of one of the central theorems of this class. I might talk a little bit about this week even. Yeah, I mean, actually, it's kind of interesting to think about the ant and how they would actually go about understanding their intrinsic geometry. I mean, it was hard for us. It took Einstein to figure it out. Like, you literally need an Einstein ant to be able to do this, right? I mean, Einstein was the first person. Like, why did we celebrate Einstein? Because he was the first ant smart enough to figure out we were on a curved surface. That's why. Right? I mean, it is like, if I put it that way, it doesn't seem so impressive. It's just like, how could all the other ants not realize it, right? Well, it turns out it's almost flat, right? I mean, if the thing you're on is big enough and your ant is small enough, right, then it's almost flat, right? And so, it turns out. And then you say, well, what's the effect of that curvature? Like, shouldn't you have noticed it? Well, yeah, we always notice the effect of the curvature. It's called gravity, right? But that's when you have curved space-time, not just curved space, okay? So just realize it's not going to fit any of the pictures I've just drawn here, right? But I kind of wonder, have I said it earlier in the class? Let me explain this, okay? And we're off the topic a little bit, but we're ahead a little bit, so we can do this. And that first week, did I explain to everyone that we're in an accelerating frame of reference right now? I think I did. Did I? Okay. And so that's what kind of throws us off, right? Yeah. And I think, did I talk about the elevator in outer space? Imagine you go into an elevator, right? And the doors close, but unbeknownst to you, some aliens from a far superior civilization have decided to kidnap you, and it was a booby trap, and you thought it was an ordinary elevator, but it wasn't. It was actually a spaceship elevator, right? And it's rigged, and so they just take the elevator straight up out of the top of the building, and you're wondering why the doors won't open, right? They've got all kinds of stabilizers on there, and they abduct you, right? And they're taking you out into deep space, right? And they can do this in such a way that you just think you're stuck in an elevator, right? And meanwhile, you're on the phone talking to some AI, alien bot or whatever, something like that, right? Telling you to just stay calm, right? And they've got your next thing, you're in deep outer space, right? You have no idea. Now, if they don't accelerate at 9.8 meters per second squared away from the Earth, then the point is you'll be floating in space, right? But they have to accelerate it at so you're in an accelerating frame of reference. They have to accelerate you 9.8 meters per second squared, going faster and faster and faster away from Earth, so that it pushes you on the floor of the elevator, so that you feel like you're still on Earth, like it simulates gravity, right? And then Einstein's great insight was, that's not simulating gravity, that is gravity, right? We are all in an accelerating frame of reference. And you can't tell the difference, so therefore it's the same thing. It's basically his philosophy. And then you might say, but wait a second, how can I be in an accelerating frame of reference? Something else is, I'm obviously not moving. Look, see, I'm perfectly stationary with respect, but with respect to everything else, which is also in an accelerating frame of reference. And so, it's a pretty deep idea. And then you'd say, well, what's a non-accelerating frame of reference? Okay, pick up a rock, throw it in the air. That's a non-accelerating frame of reference, actually. And so the force of gravity comes from, or the phenomenon of gravity. It's not even a force. Even physicists talk about the forces of nature, and they include gravity, right? But from this standpoint, it's not a force; it's a phenomenon. So, what's this got to do with curvature of space-time? Well, normally, if you think about us and people on the other side of the world, normally when you're accelerating away from each other, should get further away, right? But if you're on a curved space, that doesn't have to be the case. So the curvature of space-time is what makes it possible for two people to be accelerating away from each other and not get further apart. So matter curves space-time. And what that does is it changes what the non-accelerating frames of reference are. And another way to kind of, so here's maybe an analogy with the sphere here, is that if I have a sphere, another effect of this curvature is that if we both, two people start at the South Pole, and one is going this way and one is going that way, that eventually you come back together. A little bit like gravity, right? I mean, you're walking away from each other, and then all of a sudden, hey, good to see you again, right? And so the curvature is kind of pulling you back to your friend, isn't it? Like, but you're saying, no, I'm going straight. By the way, just like the Earth is actually going straight into space-time. The moon is going straight. Asteroids are going straight. The sun is going straight. In the space-time, as straight as it can. Right? It's on a curved space-time, right? So if you're on a lumpy potato and you're an ant trying to go straight, you're going to follow a complicated path, but you're going as straight as you can. Right? It's the curvature of the space you're on that causes this interesting dynamics. And so the curvature here is causing us to come back together, and sure enough, if you throw a rock, it comes back down. That path is because of the curvature of, well, fundamentally, everything is affected by the curvature of the space you're in. Of course, in that case, it's because we're in an accelerating frame of reference. But if you say, okay, look, let's get away from that. Let's say the sun is here, right? And I don't want there to be any frame of reference. I don't want us to get away from the Earth, right? What does gravity do? Well, if it weren't for the sun, if you're in deep outer space, then something in motion stays in motion. You just follow a straight line, right? But if there's a sun there, it's curving space-time, it's putting a dimple in space-time, and it so happens that something far away from the sun actually curves towards the sun, right? And you say, oh, gravity. And so, yeah, that's gravity. But by the way, this thing curving towards the sun would just be floating in space, and they wouldn't feel anything. They would say, no, I'm. This is the relativity part of it. With respect to their frame of reference, everything, they're not accelerating at all. They're at rest. The sun's coming towards them, arguably. Okay. So in other words, this geometry is at the heart of understanding general relativity. And so Gauss realized there was this intrinsic geometry, and he realized this was a deep idea. Like, maybe, okay, if I said Einstein was the first ant who realized we were on a curved space-time, that's true. Gauss was the first person who defined what a curved space was. Carefully, right? He just didn't realize he was in one. Right? So that already took, it took two geniuses, one just to figure out what curvature was, right? And the other person to realize, oh my God, the universe is curved. Right? And then we think of these as, these are some of the greatest thinkers. So what do we celebrate about them? The fact that they perceive something so fundamental, like how the rest of us miss it, right? All of humanity missed it prior to that. Didn't know what curvature was, and didn't realize we were in a universe that was curved. That's what is a mark of a great idea, by the way, is when after you understand it, you're like, duh. Right? It's like, it's like,
I don't know if
yes.
that's how I feel like right now.
Well, I mean, it's sort of like, once you learn the idea, then you're like, of course. Why didn't I realize? I mean, you realize your own. It's sort of like, it's not so much the idea as all of a sudden you've removed your own ignorance, right? It's I think that's what it is, right? It's like oh, okay. I see now, right? And that's so much of what we call learning, right? Is removing, is trying to just, it's trying not to be so dumb, right? And that's the thing we struggle with. We're biological creatures. It's like a dog trying to understand something, or a cat, or whatever, right? And we see them try, and it's funny, and we enjoy it. And it's like, and they can learn things, right? And we're like, oh, look, this dog is so smart. you know, and then, but compared to a human being, dogs are not very smart, right? But then compared to any reasonable reference frame of what intelligence should be, right? None of us are very smart, right? We're just these biological entities, and amazingly, we can actually learn some things, right? And so it's great that we can learn at all, right? And so humans are super cool that way. But if we meet an alien civilization, I think we're going to find out that we're not as cool as we think we are. I just have to, I mean, especially if they come to us, right? And that would be cool. I mean, I think it's undeniably the case that we're just at the beginning of what, we're just now scratching the surface of what intelligence might be, right? And I think we're also, by the way, I don't know what you guys think, but we're liable to be humbled by artificial intelligence too, in the not too distant future. Now, that we'll see if that actually happens. I mean, that's an interesting question. Are we smart enough to actually make something smarter than us, right? But some people are starting to think maybe, right? And we can definitely make artificial intelligence dumber than us, right? I mean, so far it's dumber than us, right? But it's kind of like, oh, okay, that almost seems like a person, right? How about this? We can make AI smarter than some people. I think that's true. Unfortunately, all right? I think AI is now smarter than some people, right? And unfortunately. And so like that's a little bit of a wake-up call for the rest of us, right? Because like, wait a second, how much smarter are we than those people again, right? And then AI doesn't ever get dumber, it only gets smarter. And then we die, and then we have to start all over and teach the baby and how to do everything, you know what I'm saying? So that AI doesn't, right? And so, I don't know, that's, maybe, I guess if you had to bet, AI is probably going to humble us. Hopefully it doesn't destroy us, by the way. Are you guys afraid of AI, or do you think it's going to be a wonderful benefit to society?
Skeptical.
Huh?
A little skeptical.
A little skeptical?
Yeah.
More fear than anticipation?
I think it'll be fine.
Do you think it'll be fun?
Yeah.
Okay.
It'll be like our little companion. It'll be fine.
I think it'll be fun too. I think it's just driven by DC hype cycle.
I hope you guys are right.
Still put in charge of the power grids and stuff.
Don't put in charge of the power grid?
Yeah, you can
Okay.
always pull a plug.
But they can make videos.
We can
now.
make videos too.
Yeah, but like,
They can.
the videos are only gonna get better and better, so.
You know what is, okay, I was actually listening to a podcast, I'll go, okay, and so this guy, it's on Lex Friedman, you guys watch Lex Friedman?
Oh, yeah.
Yeah, and there's one of the most recent ones is this guy who went by the alias Beth Jesus.
Okay.
All right, and he was being interviewed. Actually, a surprisingly interesting guy. Anyway, and he was talking about artificial intelligence, and he's dedicated his life to thinking about a lot of these things. And he says, "Don't be afraid." Says, "Don't be afraid." And he's like, this will be a good thing for humanity. And so, all right. But him telling me not to be afraid makes me a little more afraid, because it's like, yeah, people like him are like going to get us to put our guard down, right? And then next thing you know, something bad can happen. And then Lex Friedman pushed him on and said, wait a second, but what is the worst thing that could happen? And then I think they actually did utter what the worst thing that could happen. And this is a realistic thing. It's not so much the Terminator scenario. It's where they take over and destroy the world. It's where a very few number of people get control of the AI and dominate the rest of us, and we don't even realize we're being dominated. And so you get more of a George Orwell future where it's mind control, and they might even, next thing you know, complete victory would be where they raise the next generation to believe that AI doesn't even exist, right? And then you have, people in charge of the AI to control the society, and you have a very, very small number of people controlling a very large number of people, right? I think, in other words, it's not so much AI taking over humanity, it's evil people who have always existed, right? Using AI for evil purposes, right? That is super realistic. Like, do I think evil people will exist in the future? Of course they will, right? They always have existed, unfortunately, right? And so, can we make sure that AI stays sort of distributed, right? Where it's an equalizing force among human beings as opposed to making the powerful even more powerful, right? Okay. Sorry for that. We're having a fun discussion today a little bit, okay? We have a test on Wednesday.
Next Wednesday.
Next Wednesday, not this Wednesday. But we're a little bit ahead, so I guess we have the flexibility. Okay. Anyone make any final comments about the end of the world with AI or anything like that?
I haven't heard that last theory before, but that's actually scarier
Yeah.
than like the idea of them optimizing and destroying humanity.
Very realistic
Yeah.
that bad people, in fact, someone commented recently, you guys have heard of Putin,
Oh,
Yeah.
leader, dictator of Russia. By the way, all the Russians I know, great people, right? Putin, scary guy. Has people killed. Now, our leaders sometimes have people killed too, so I don't want to be a hypocrite here, right? It's tough being a leader. But nevertheless, how about this? There are people, wherever you think about Putin, there are people in the world who are scary, right? And who are dangerous and might be doing things against our interests, right? Whether it's Putin, we can get into a debate, blah, 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 right? But one of the most powerful things that Russia has going for them is they're a big oil producer, right? So who's to say, and we all know that they're into hacking and stuff, computer hacking, right? I mean, they've got hackers. I mean, well, look, not as many as we do. Okay, let's keep it real here, right? NSA, right? Our NSA is the biggest employer of mathematicians in the world. Okay? But anyway, every major country has hackers, right? Trying to hack things, right? And so it's in Russia's interest to get other countries as dependent on them as oil as possible, right? And so, are they already employing AI and other hacking and other ways of trying to influence other societies to become more and more dependent on their oil? You just have to ask the question, right? Wouldn't that be a logical thing? If you were Putin, wouldn't you do that, actually? Like, why wouldn't you do that? Right? I assume it's going on. Okay.
So about this ant. So does the
Yeah.
ant know? So the ant can tell its like intrinsic curvature for sure. But does the ant have any way of finding out like the topology of its universe? Like if it's on a sphere, right?
Yeah, I mean, ants, they take a topology course. What's that math for 11 here at Duke? Then they can. There's work to do, right?
Right.
Math for 11 is not a trivial subject completely, right?
Mhm.
But they can triangulate their surface, right? They can put down markers and then say, okay, here I have a triangle, here I have a. You know what I mean when I say triangulate?
Right.
Like they can create little triangles that cover the whole thing and then map it out, and then they can compute all the different topological invariants of their surface, right?
Uh-huh.
Right, from that data, right?
Mm.
And so they can detect the topology, they can detect the geometry.
Do we as humans have any way of doing that with our universe? Like, do we know what our universe looks like topologically?
That's a great question. What is the topology of our universe? Is a great question, and we don't know. It's just that we're on such a small part of our universe. It's so like imagine a very, very big potato, and we're just on a very small part of the potato, right? And then someone asks us like, does the potato have a hole in it over here or something like that, right?
Oh, yeah.
Well, I mean, I don't know, right?
Mm.
But we see that our little part of the universe seems to be topologically trivial. At least we haven't detected any topology so far. The one exception might be black holes. Black holes, we think of them as a sphere of no return, but actually, when you do mathematical models of what's inside a black hole, you can get topology. And so, I suppose it might be, and how many black holes exist in the universe is thought to be really large numbers. So, the center of every major galaxy seems to have a supermassive black hole in it. I think the one at the center of the Milky Way galaxy is something like, is it 4 million times? No, 4 million times the mass of the sun, I think. And we're aware of, and so we've come to the conclusion that most of these big galaxies have black holes at their centers. By the way, it's not like, people talk about the stars in a galaxy orbiting around the black hole at the center. The black hole still represents a small percentage of the mass. So it's not like a solar system in that sense, right? Everything's rotating around everything else in some sense. But the black hole is at the center simply because is sort of formed by everything sort of falling in towards the center. Everything that fell into the center tends to get into a dense configuration and forms a black hole. It's the general thought. But it's interesting that you mentioned about this understanding the overall geometry and shape of the universe. There's something called the Hubble tension, and that shows that we don't really understand the geometry of the universe perfectly. Okay, so general relativity and our assumptions about the universe give a very good approximation about the Big Bang and the accelerating expansion of the universe, but not a perfect approximation. And if I can remember, I'll send you all an article that came out recently with a competing theory that sort of is an improvement on the standard Big Bang theory. Because there's all kinds of ideas that are still being considered. Okay, so anyway, that's okay. All the discussion we've had so far is Gauss curvature, right? Which I just wanted to summarize a little bit before we go into mean curvature, right? So Gauss curvature, in some ways, is curvature. That is what intrinsic curvature is. So if you're an ant on a potato, there is just Gauss curvature. If you are, if you're us in a space-time, right, in a universe, there is just Gauss curvature and its generalizations to higher dimensions, okay? Which is a bit complicated, but actually, let me tell you that story just really quickly, okay? What is curvature of a space-time? Okay? Actually, it really is just Gauss curvature, but generalized. So how is it generalized? It turns out Gauss curvature is inherently two-dimensional. Okay, so there is a term, if you Google it, yeah, there's a 3- and 4-dimensional Gauss curvature. Ignore that. I've never used it in my entire career. Okay, it's irrelevant. It shouldn't be called Gauss curvature anyway. To me, it's just like, okay, I don't like the terminology at all. Okay, because it's not intrinsic geometry even. Okay, so that bugs me. Okay, so how Gauss curvature generalizes in higher dimensions is, let's pretend like the world was 3-dimensional. Okay, so let's ignore time for right now. Do you guys mind? It's a little bit easier for our brains. Okay, so and imagine the universe was just 3-dimensional, so we're like at a fixed instant in time. Okay, so what Gauss curvature is if I point in this direction and I point in that direction, y'all see that any two vectors define a plane, right? The plane going through those two vectors, right? And then what you can do is, let me show you all something called the exponential map, which is, I don't know, it's probably a barely okay name, kind of stupid actually, all right? But what the exponential map is if I have some surface, and then I have the tangent plane here, right? This maps, it's a mapping. What it does is it maps the tangent plane to the surface itself, okay? So it'll give me any vector here, v, and then what I can do is say that exp of v equals the point q. Okay, let's start at the point p, right? So this would be base at the point p. You give me a vector v, what I do is I simply go in that direction for that distance, okay? And this gives me the point q. Do y'all see that this distance right here is the same as the length of that vector there? Y'all see the idea? It's a very natural mapping, isn't it? Do you guys agree? And now I have a locally one-to-one mapping between this tangent plane and, for a sufficiently small v, right, this is going to be a one-to-one mapping onto my surface, right, or my manifold. That's called the exponential map. Now, it's not going to be one-to-one once it starts looping around and stuff like that, right? Then it's going to be, it's still well-defined, right? This is always well-defined. It's just going to, it's going to be multiple, it's going to start overlapping itself, right? Two different vectors could go to the same point, conceivably. Okay, well, guess what? If I pick two vectors in a 3-dimensional thing, any two vectors defines, I'm really picking two vectors in the plane here. I'm saying go this way and go that way. That's like a v and a w, right? And then I can say, what's the exponential map of any linear combination of v and w? And that gives me a surface in the curved space. Now, in this picture, by the way, that would just be the whole 2-dimensional surface, right? But imagine this was a 3-dimensional surface here, right? We call it a manifold. And then I could still pick two vectors, right? Linear, and so this would actually be a 3-dimensional, this is a 3-dimensional flat space here. I'll call it R3. The tangent plane is topologically R3. If I pick any two vectors, that gives me a 2-dimensional plane, right? I can then take the exponential map of that 2-dimensional plane and I get a surface sitting inside of the 3-dimensional manifold. You guys agree? that surface has intrinsic geometry, and you can talk about what's its Gauss curvature at the point P. Okay? So here's the point. For any two directions I choose, I get a Gauss curvature. Really, for any hyperplane I choose, I get a Gauss curvature. Okay? Think of it. That's a little. But how many different how many two-dimensional planes are there for me to choose? Well, quite a few, aren't there? Right? So for every two-dimensional plane I can choose in the tangent plane, I get a Gauss curvature. Turns out that's all curvature. All curvature in higher dimensional space is just understanding the Gauss curvature in every two-dimensional plane. So in other words, what you learn in this class and your intuition about Gauss curvature can be generalized. We just call it sectional curvature. Right? So given any two-plane, you talk about the sectional curvature of that two-plane. It should really be called the Gauss curvature of that two-plane, but they call it sectional curvature. And turns out that sectional curvature completely characterizes curvature in higher dimensions. We typically think of curvature in higher dimensions, and that's not necessarily the most convenient algebraic way to do it, but in terms of the picture, that it captures all the information. All the information is encoded there. Any questions before we move on? Yes?
When you said that define that the tangent plane is a vector space, how do we know it passes through origin?
Say again what?
Like we have said that tangent plane is a vector space.
Yep.
And we never really said that it must pass through the origin. So how do we
Oh, I mean, in the pictures I'm drawing, I mean, this right here is the origin of the tangent plane. So we just define it to be that way.
Oh.
Yeah. So whenever I'm drawing this picture, this is the origin of the tangent plane. Yeah. Yeah, and so you just everything is with respect to that.
Okay.
Yeah. Okay, let's do main curvature. So what I mentioned last time is that in the same way that K is the determinant of the shape operator. Now the shape operator is not intrinsic geometry, but remember the shape operator has eigenvalues K1 and K2. We define H to be half the trace of the shape operator, so that's K1 plus K2. We have all kinds of formulas for it and so forth. And outside this class, mean curvature H just equals K1 plus K2, but in this class and in every other curves and surfaces class, they define it to be 2H. And so you can do some examples like a surface of revolution. And the surface of revolution, here we have take the xy plane, take some curve, g of u, comma of h of u. Normally we were using s, but we want to use u here because we're going to have u and v coordinates for a surface here in just a second. And then what you do is you go ahead and add a third dimension and then rotate around the x-axis. So we've done this before with the when we were computing. I forget, where were we computing before? We did surfaces, or just examples of surfaces, right? Surface of revolution. We showed how you could parameterize it. Now, there's a couple of things. If this was a level straight line, then we get a cylinder, right? By the way, if it's a vertical straight line, you get a plane. Do you guys agree? If it's a perfectly straight up line, you rotate around, you get a plane, right? If it's a straight line like this, we get a cone, right? And it turns out you can compute what the mean curvature is. And it turns out h is exactly equal to, you guys have done these types of computations, minus h double prime plus 1 plus h prime squared divided by 2h. Oh, sorry. When we rotate around, I forgot to parameterize it. Yeah. So instead of doing it like this, let's do it as, instead of using u, just use w and h of w. So we're going to suppose it's a graph, okay? And so, now you might say, wait a second, if it's a graph, it means that you're not allowing it to go vertical, right? And that's right, we're not going to let it go vertical. Now, on the other hand, if it does go vertical, it just gives us a plane locally anyway, right? So let's suppose that we're looking at, in fact, here's what's kind of interesting. we're going to suppose that it's not vertical. In other words, we're going to suppose it's a graph. And then we're going to be able to prove that as long as it's not a plane, as long as it's not vertical everywhere, then it will be a graph, actually. Okay, so, but just assume it's a graph for right this second. Then what you get is the mean curvature is equal to, here h is a function of w. H prime w squared to the power of 3/2. And what we're going to do is we're going to set this equal to 0. Let's find all minimal surfaces. Okay, so when you set h equal to 0, remember that's called a minimal surface. We explained that last time. It means it locally minimizes area, as it turns out. We'll talk more about that. And so we can multiply through by this fraction here on both sides. And so then we get an ODE. And the ODE is just that h times h double prime is equal to 1 plus h prime squared. You get this second order ODE. And you can solve that second order ODE. The book does it in some detail. And what you get then is that h is equal to 1 over for some constant c and d. It's basically a hyperbolic cosine. But by the way, this is a hyperbolic cosine where you rescale it by a factor of c in the x and y directions. Okay, if you like, this is y equals. This is like, it's ch, right? So cy equals hyperbolic cosine of cx, right? So this is scaling in the xy direction is the same. So it's a hyperbolic cosine. Hyperbolic cosine looks like this. But then also scalings of it, I can make it twice as big this way or twice as small. And then when you rotate it around the axis here, you get what's called a catenoid. Okay. So it's a catenoid. And then you also could shift it left and right, so you can put in a plus d here. Okay. And so it turns out that all minimal surfaces that are graphs are of this form. Okay. Is your question?
Yeah, I was gonna say, so when we have the equation of that graph up there,
Yep.
and we're using h in that, what exactly is that saying for like the second coordinate of our graph?
Oh, this right here?
Yeah.
So what we're saying is, rather than looking at all possible curves, which might be a spiral or who knows what, right? Imagine you have y equals h of x, right? In other words, y is a function of x. That means you have to pass the vertical line test, right?
Yes.
Okay. The way you parameterize this is like that.
Okay.
So this is how you parameterize a curve in the xy plane, y equal h of x. You most easily parameterize this way.
Okay.
Okay, so we've made an arbitrary assumption. The arbitrary assumption is that the thing we're rotating around the x-axis is a graph over the x-axis. Okay. Now it turns out, without lots of generality, that is all cases where you set h equal to 0. Why? Because if h equals 0, you satisfy this second OD. So all you need then is you say, suppose that's not vertical somewhere. As long as there's one point where it's not going straight up, like right here, it's not going straight up. It's not going exactly straight up, right? If there's one point where it's not exactly straight up, then you can prove locally that it's a graph, and therefore it equals a catenoid. But if you're a catenoid, it's always a graph. So if at any given point it's not exactly vertical, then it's locally a graph. Therefore, it's a catenoid there. Therefore, everywhere it's a catenoid. Okay? On the other hand, if it's completely vertical at one point, all bets are off. But if it ever becomes anything other than vertical, right, then it's a catenoid. And so the only other possibility is that it's vertical everywhere, which in fact is a straight line, which gives you a plane. Okay, so if you take a complete straight line, a curve going straight up like this, and then rotate it around, right, then what you get here is a plane, right? You say, so I didn't draw it very well. You take a vertical line and rotate it around, you get a plane, right? Okay, so basically all surfaces of revolution that have h equals 0 are either a plane or a catenoid. That's the argument. So cool stuff. here's a random, here's a tangent on the catenoid. Yes, question?
So this is only for surfaces of revolution.
Just for surfaces of revolution.
But it's only for the surfaces that have like G of U is equal to U. So if you have a graph that is in R3 and then you revolve it around one of the three axes, then you can't have, then you're going to have G prime in your formula rather than just one, right?
Okay, I lost you at some point, but okay, so if I have a graph in the two-dimensional plane,
Well, I mean the formula for H in the book, instead of having in the denominator, for example, 1 plus H prime squared, it's G prime squared plus H prime squared. But in this case, when you're just drawing a two-dimensional graph and then rotating it around one of those two axes, then G prime, or G of U, is just equal to U, because you can parameterize
yeah. So this is an example where G of U equals U, right? And we're using,
So this is not general to all surfaces of revolution. This is just a surface of revolution for a curve that's in 2 dimensions. And then you add the extra dimension.
Okay, so let me summarize. All surfaces of revolution come from curves in 2 dimensions.
Okay.
Okay, by definition, right? So you take a curve in the xy plane, then you add your z-axis coming out of the board, then you rotate around the x-axis. Okay? Now, it turns out, yes, we could parameterize it this way, and I think y'all might have had a homework exercise where you do that, and you compute k, you compute h, and all that, right? But it turns out we don't need to consider all possible ways of parameterizing all possible curves. We can restrict to this case, and then we end up proving that all but one minimal surface it falls into this case. This makes it a little bit simpler for us to solve the equations, right? Had we used this parameterization, we would have gotten a more complicated equation here, right? It wouldn't have been an ordinary differential equation, because where it wouldn't have been, there would have been 2 unknowns, G and H, right? And so we can simplify and say, look, let's just look at things that are graphs. Let's look at where G of U equals U, and H of U could be whatever you want. And let's parameterize it by W instead of U. When you do that, you just get an ordinary differential equation. Okay? How do you solve ordinary differential equations? Take Math 356, whatever writes in the book, solve it, right? It's its own art form, right? And it turns out here's the answer. And then you can say, oh, okay, that's just a shifted, scaled shifted hyperbolic cosine, and that's what we call a catenoid when you rotate it around. And so this shows that at any point your surface is locally a graph, it's a catenoid. But what's the other possibility? Well, at every point, it was never a graph, right? Every point, this curve is vertical at every single point. Well, it must be a line going straight up, and that gives you a plane. And so those are the only minimal surfaces which are surfaces of revolution. Now, surfaces of revolution is a very restrictive subset, by the way. Very restrictive, right? In general, if you want to know what a minimal surface is, it's a soap film, right? Take a piece of wire, take a circular piece of wire, dip it in with a handle, dip it in soap. When you pull it out, there will be a soap film filling in the circle, right? Be a disc. Now take the piece of wire and step on, stomp on, and twist it. Right now you got this all bent up piece of wire, right? Dip it into the soap, pull it out. You'll get, nevertheless, a minimal area surface spanning it, right? And so it'll be sort of twisted around as well, right? But it's going to be nice and smooth, and that's called a minimal surface. So actually, the number of minimal surfaces is quite large. Any bent piece of wire you can come up with will give you a minimal surface. Okay? Pretty cool stuff. Now, you might say, but wait a second, what about soap bubbles, right? We all love soap bubbles. Well, it turns out soap bubbles are constant mean curvature surfaces. And one of the best soap bubbles is when you have 2 soap bubbles touching, right? And so you might have a volume of air V1 here and a volume of air V2 there, right? And so you have 2 soap bubbles. Of course, by themselves, they might be just they might just be spheres, right? But then the soap bubbles can touch, and then they form a configuration like this. That's called a double bubble. You may have seen one before. And it was only like less than 20 years ago that a friend of mine proved that this is actually the minimal area configuration for 2 trap volumes of air. Isn't that interesting? It's actually a pretty hard problem to prove that minimizes area among all configurations that trap 2 volumes V1 and V2. Now, given 2 separate volumes V1 and V2, the fact that it's a sphere has been known for some time. Right, so, since the 50s or earlier. I mean, at least. And that's interesting as well. And what they have in common, though, is that we know a sphere has constant mean curvature, but also this does too. So the mean curvature of this surface here, it might be C1. The mean curvature here might be C2. And actually, this boundary surface here is not necessarily a plane. If E1 and V2 are not equal, then H here is also a constant mean curvature surface, has mean curvature equal to C3. So you take three constants. And there's a relationship between C1, C2, and C3. I think the difference between C1 and C2 is C3 up to a sign.
So you were saying he proved that any like natural formation of a double bubble minimizes the area of like that.
He proved that if you that all double bubbles in nature, which minimize surface area, are of that form. Yeah, I think C1 minus C2 equals C3 or something like that. Yeah,
That's
it's pretty cool. I mean, every child who's ever blown a bubble knows that's the answer, right? You just blow bubbles and see them stick together, and you can see it, right? And you're like, oh, okay, nature knows what it's doing. It's minimizing surface area, right? And so everyone believed this conjecture to be true, but rigorously proving it turned out to be quite challenging. By the way, the triple bubble configuration conjecture is still wide open, I think. I'm not an expert on bubbles, but I think it's still open, actually. And then, of course, you ever do a soap film where you see, like, it's not two, it's not three, it's like hundreds of bubbles, right? And that's like a bubble bath, right? I mean, intimidating. I don't know if anyone even has a conjecture what I don't even know if people have a conjecture what the answer is there, right? But we see it's okay. But what we do know is that each of those surfaces are constant mean curvature. They're constant mean curvature. That much is known, okay? But what's the overall configuration? Complicated. And the reason that mean curvature is important is because of this thing I already said last time, which is that it's the rate. Do y'all remember I wrote down this formula? The rate of change of area is equal to the integral of your surface of the mean curvature times how fast you're flowing out times the area form. And you compare that to the rate of change of volume. This was the shell method. This was integral of eta times dA. So if you have some surface, and then you flow out with a perpendicular speed, right, eta, and you say, hey, how much more volume am I at? The surface is clearly getting bigger. And if I look at the volume on the inside, what's the rate of change of the volume? I can probably persuade you by some shell method that that's the answer, right? The rate of change of increase of the volume is integral of the speed that you're flowing out perpendicularly times the area form. That's the thing you integrate to get area, right? Well, how about the surface area? How's that changing? Well, it's the same formula, but you put a factor of h in there. Okay. Actually, in this class, it's a factor of 2h. I think, in fact, it's negative 2h, okay, to get the conventions right. Sorry. In every other, outside this class, it's h, possibly negative h. Again, this is where I think we have the mean curvature of the sphere is negative 1 over r, and that if you have the normal pointing out, I think. Okay, so the point is this negative 2h is equal to 2 over r for a sphere of radius r to establish the convention. And so the ratio between the rate of change of area and the rate of change of volume, right, you see they're the same except for the factor of h. And so that's why h has to be constant, because if otherwise what you would do is, if you're trying to minimize area, right, if this ratio wasn't constant, then I could, wherever h was low, I could flow out faster where h was lower and then it'd come in where h was smaller, right? And the total volume wouldn't change, but the area would change. Okay? And that idea, by the way, is called calculus of variations, or it was one of the key ideas of calculus of variations. And that's the idea of calculus of variations without the calculus. Okay. So when we look at constant mean curvature surfaces, they're interesting. Constant mean curvature. And that's the same thing as we're doing here, except instead of saying it equal to 0, let's set it equal to a constant, okay? And so just h equal to some constant. The book uses c. And of course, what does that give us then? Then it gives us a very similar ODE. It gives us that 1 plus h prime. It comes from that same formula. Okay, same setup here. Surface of revolutions, but some constant times h times 1 plus h prime squared to the 3/2. So you'll see that if we set this equal to c, right, and then multiply through by the denominator, then we get this here for some c. I guess the 2 got absorbed into that c there. And so then you can say, okay, well, how do I solve this? This is a more complicated second order ODE, but you can still solve it explicitly. The book does it. It's not easy. And the book gives you some formulas for it. I'll refer you to the book. Let me just get to the pictures. Turns out you get stuff that looks like this. And when you rotate it around, you get what's called a Delaunay surface. And so it turns out that these surfaces have h equal to some constant c. Okay? Now, let me tell you what I particularly like about these Delaunay surfaces. Is that they are, there's something quite beautiful about this. I mean, first of all, the fact they oscillate like that, when you see a second order ODE, you kind of think, oh, sines and cosines. I mean, you know, if I say h double prime equals minus h, right, then that solution is, you know, sine of x and cosine of x have that property, right? So, you know, oscillatory behavior is not unheard of with second order ODEs. Obviously, you can't just assume that from that. But anyway, it's not shocking that we get an answer like this. But what's kind of interesting geometrically is that, would you guys agree that a cylinder is both a surface of revolution and has constant mean curvature? Right? So yeah, obviously that has constant mean curvature, right? That's one extreme here. When I get all the oscillations out, right, I just rotating a line, I get a cylinder, right? But now let's say you maximize the oscillations. It turns out when you maximize the oscillations, it ends up looking like this. And then when you rotate these things around, there's your axis, right? When you rotate these things around, you get a necklace of spheres. Turns out these are exactly spheres. And we know that spheres have constant mean curvature too. So Delaunay surfaces interpolate between cylinders and spheres. Isn't that neat? I mean, if you look at this right here is halfway between that and whoops. It's amazing how far off I was on that. Wow. Anyway, I'm regretting doing that at all at this point. Okay. That and, okay, let me try again here. Right, and then the point is, these Delaunay surfaces are interpolated between these things that when you rotate around, you get a necklace of spheres, and the straight line, which is giving you just a cylinder. But wait, there's more. Wait, there's more. There's something called the roulette of a parabola. You guys have homework exercises on this. Is this what I was doing Friday, I think? To mess around with this stuff to some extent. And this is quite amazing. And all I can say is, people have been sitting around thinking about this stuff for quite a long time to notice this. It's like, or was it the last homework, or is it this coming homework? The coming homework. Okay. So, I mean, if you take a wheel, right, and then you look at the center point, and then roll the wheel. The wheel is like a wheel of a truck or whatever, right? If I roll the wheel, right, going forward, the center point here traces out this straight line, which when you rotate around gives us a cylinder, right? So this leads to a cylinder. Okay? When you rotate it around, right? Okay, that's easy to see. I see that. So what, right? Okay. Well, now suppose you have a really weird shaped wheel. It's a line segment. Okay? And now I look at one end of the line segment, and like, why would someone use a wheel that's a line segment? Okay, well, just go with me for a second, okay? And so it's a stick, right? And there's no friction, okay? Perfect friction, or there's 100% friction, no sliding. And so then what this traces out then is a part of a circle, right? And then the stick is like this. And then the stick comes over like this, right? And then it comes back up like this, right? and now the stick's like this, and then the stick rotates around like this. Now this point is staying here the whole time. And now what you see is, oh, I get a series of half circles, which when I rotate around, give me spheres, right? So then when I rotate around, these gives me a necklace of spheres, right? Okay, so in other words, whether I have a circular wheel or a stick as a wheel, right? But then look at the endpoint for some reason, I can get these two extreme situations, can't I, right? But wait a second, a stick and a circle, what do they have to do with each other? Can anyone tell me what a stick and a circle have to do with each other? Is there any connection whatsoever?
Squeeze this.
They're both ellipses. Right? I mean, you have these things called an ellipse, right? And they have one focus or two foci. When you have, and you know, what are the extreme points? Well, you have a perfectly round ellipse. That's where the two foci are the same point. And then you start to squish the circle a little bit, and then the foci separate. And in the most extreme case, when you squish it entirely, the two foci are the two endpoints of a stick. Okay, that's just a really, really the maximum eccentricity ellipse. And now here's the crazy thing. And what kind of person doesn't have the life enough? Who's sitting here doing these computations, right? Mathematicians, that's what we do, okay? But I mean, it's pretty cool that someone noticed this, right? Delaunay, supposedly, I don't know. And so pick one of these foci, and then look at the path that when you use this as a wheel, just pick one of them, not the other one, okay? And then look at the path that it traces as you do it, and you get this Delaunay curve here, which when you rotate around has constant mean curvature. Who knew? Well, it's a coincidence. It's a mathematical coincidence that the curve that this traces out satisfies this second order OD also. So in other words, when you're interested, when you look at an ellipse and you do the wheel thing, right, and look what that focus traces out, that gives you the same curve as the curve which when you rotate you get constant mean curvature. And as far as I can tell, it's just a mathematical coincidence, but it's not cool. It's a cool mathematical coincidence.
I wonder if that's related to like Kepler orbits, how like because the distance from the focus to the ground is the same as like if you were a planet orbiting in an elliptical pattern to the planet, and that's a natural path that something takes under gravity. That's
I don't know.
the same.
I don't know.
It feels the same.
That's something to look at myself. Yes.
Why does it not matter that, like, looking at the stick, for example, like the two overlapping necklaces of spheres have different radius? It doesn't. And yeah, it still has.
Oh, ask your question again.
Like looking at the necklace of spheres for the stick, those two like overlapping necklaces have spheres of different radii. But
Oh no, they're the same.
Oh.
My picture's bad.
Okay.
Sorry.
Cool. Oh,
Yeah,
okay, I guess
because
it
the
makes sense,
stick length of the stick is the radius of the circle in all cases.
Yes.
It's supposed to be. My picture's not perfect. Other questions, comments? Okay, you've heard of conic sections, right? What do they call them? Conic sections, right? You take a cone. It's like a light cone from special relativity, actually. You take a cone, and if you cut across like this, you get a circle, right? If you cut across at an angle, you get an ellipse. If you keep on going, you cut across like this, where you're cutting parallel to this line here, you get a parabola. And then if you rotate more, and you cut anything in this range where you intersect twice, you get hyperbolas. Right? And so, general rule of thumb is anything that's true for, and so that's what I call them conic sections. Algebraically, you'll see that there's a lot of similar formulas for circles, ellipses, parabolas, and hyperbolas. But basically, they're kind of in the same family of two-dimensional shapes. And so guess what? This is not only true for an ellipse, it's also true for hyperbola. Okay. It's also true for parabola. What does it mean? It means if you take a parabola and rotate it, and then a parabola, take a parabola, look at it has just one focus point, and then you use it like a wheel. Whoops, I missed that. But anyway, you guys know what I was trying to do. Use it as a wheel. And then if you trace what this path will follow, what you'll get is a surface, which when you make a surface of revolution out of it, will have constant mean curvature too. And in fact, I think this will give you a catenoid, which we already did. Okay. Now notice you'll never make a complete revolution of a parabola, right? It's infinitely big, right? So you will now, what it means is when you go a distance s here, right? You have to go up a distance s here because there's no slipping, right? And this point will be tangent to that point. And I think you have a homework exercise with the parabola to show that this focus will in fact trace out a catenoid actually. And so, but by the way, what is a parabola? A parabola is the limiting case of an ellipse. Do you guys see that? Look at the conic section thing, right? Ellipse, 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 parabola, right? Like all of a sudden it's a parabola. Like it's like an infinitely big parabola. A parabola is an infinitely big ellipse. It's like where the other end is just infinitely far away. And then you go again, and it becomes a hyperbola. So maybe this isn't that surprising. That should be because these are all constant mean curvature. So the parabola is going to be constant mean curvature. But on the other hand, it's a special case, right? And that special case means that you actually have an h equals 0 surface of revolution. And then if you go to also you can do this thing. And suppose this is an ellipse, you will also get constant mean curvature, but that constant will be negative. The sign of the mean curvature will change. Okay. So if you have a convention where this is positive mean curvature with utility surfaces, then with an ellipse you'll get negative mean curvature, and the parabola gives you the 0 mean curvature, which is the catenoid. And look, why would we assign homework problems to get you to do this, to compute this? I think the general philosophy is that which does not kill you makes you stronger. It's just fun with geometry. I mean, sometimes it's just math for its own sake. And as someone who has a joint appointment in the physics department, I can say there's merit to this, okay? I actually do care about application, but it's a way to practice your mathematical skills. Okay, it's a way of think of these as test problems. Let's put it this way. The problems that mathematicians and professors and textbook writers can come up with are far easier than the mysteries of the universe, right? And so it's like, okay, at least we know the answer in this case. Like you'll know if you get it right. Right, and so it's a nice challenge. I mean, just to give you a little bit of a hint when you're trying to do the roulette of a parabola. What's going on here is you take your parabola with where the focus is, and what you're having to do is you're gonna take this parabola. Now, how do I figure out how it rotates? Well, what you know is figure out what the tangent line is. Go out a distance s, pick that point, find the tangent line there. And then you have to do a rotation and translation of this parabola so that this point here ends up there, and the tangent line is completely tangent here. Okay, so think of it as take this point and the tangent line and map it to this point here, and that tangent line exactly a distance s away. Okay, and that's how you define the roulette of a curve. Okay, and the book has a bunch of calculations relating to it. And so, I think I recall that's one of the more challenging problems on the homework. And, I would, work in groups. And of course, I'll be available Thursday to talk about it. So start early. And if you can't get it, come to my office on Thursday. I can try to struggle through it with you. And, but even better, work in groups, talk to your friends. Make sure you give yourself time to think about these things. And try to get most of the problems on each of the homeworks, I would say. That would be a good thing. Just for your confidence, if nothing else. Like if you don't get the hardest problem on each homework, it probably doesn't really make that much difference, actually. But, it's nice to give it a shot. It's kind of fun when you do get it. Any questions? Okay, see you guys next time.